Hello, everyone. Welcome. Welcome to the final colloquium of the year. There will be another one starting next semester, January 10th. For our final colloquium, we get to have Eyal Lubetzky. Eyal Lubetzky. Am I saying it right?
The first one.
First one is better. He received his PhD in 2007 at Tel Aviv University. He was then a postdoc, Microsoft Research, and then became a career researcher at Microsoft Research in 2007, 2014. Now he's a professor at NYU. In 2013, he won the very prestigious Rollo Davidson Prize. It's given to young career probabilists. And he's a fellow of the IMS and has received an AMS Centennial Fellowship. I think I'll let his work speak for himself. Yes. Very glad you know.
Okay, thanks, Elliot, for this kind introduction, and thank you for the invitation to come here. It's wonderful to be here, my first time here. I'll be talking about recent progress on the dynamical phase transitions for the 2D POTS model. I'll try to keep this talk at an introductory level. There are lots of questions that remain open. The title here has 2D, mostly because in 3D we know very, very little. And even in the two-dimensional case, there will be many open problems. Feel free to ask me questions and interrupt as I go along. And most of the recent progress that I'll be discussing is, most if not all, is joint work with my graduate student, Reza Gaisari, who is applying for jobs now. Okay, let's start with the Ising model. This is an old joke where someone introduces the Ising model and puts up a picture, and that picture is not Ernst Ising, but rather Wilhelm Lenz, who is the one who introduced the model in 1920 and gave it to his PhD student Ising as a problem to work on. And this is the motivation of the model. You were trying to model the phenomena of ferromagnetism, where you take a piece of iron, a slab of iron, and stick it in an external magnetic field, turn the field on, turn the field off, and ask yourselves whether what you're left with is a regular slab of iron or whether it's a magnet, whether it retains some of the magnetism from the magnetic field that you placed it in. And the answer, this is a well-known physical phenomena, it's that it depends on the temperature. And there is a critical point. If the temperature is high enough, then the iron does not remember that it was subject to a magnetic field. And if the temperature is below that critical point, called the Curie point, then it does retain some residual magnetism. And that's the model that's the phenomena that Lenz was after when he tried to propose a model. And the idea is that magnetism is caused by, it's a collaborative effort of the atoms spinning in the same direction, or mostly in the same direction. So you have a global phenomena, whereas atoms only see the atoms next to them. And you're trying to create a toy model that would capture how local interactions, where you only see your immediate neighbors or affected by your immediate neighbors, can lead to a global phenomena, because you see your neighbors, and they in turn see their neighbors, and so on. Okay. And ever since let me skip here. Ever since the first paper by Ising in 1925, the fact that the model that Lenz proposed was, on one hand, so simple, and on the other, did manage to capture this phenomenon of ferromagnetism, the model became extremely useful to study various phenomena where you have local interactions. It can be, I placed in a bunch of fields, and you're trying to just understand how a cascade of interactions between particles, between entities, will lead to a a global phenomenon. Okay, so occasionally I poll and see how many papers have the word easing in their title. So it's arguably the most studied model in math physics. This is the easing model. And this talk will be mostly devoted to the natural generalization of the easing model to the Potts model. So this is, again, not Potts, but his advisor, Cyril Dom, also the one who came up with the model, gave it to his PhD student, and this is Potts. And the case Q equals 2 is the easing model. The easing model was a model where each atom could spin up or down. So it had two possible states. The Potts model, as you'll see in just in a few seconds, just generalizes it to having not two states, but Q states. And each one is now a column. Okay. And the Potts model is intriguing because it is, you have a very, very simple formulation of a probability distribution, and it comes packed with first and second order phase transitions, as we'll soon see. Okay, so what is the classical easing model? Let's start with that, and then the generalization to the Potts model would be immediate. It is nothing but a distribution over giving each atom either a spin up or a spin down. So we have two possible states, plus and minus, or blue and red. And usually when I say 2D, we think of these atoms as being positioned on the vertices. These are the vertices of a square lattice, an n by n grid. And there could be, you can think of it, it's best to think of it for most of this talk as being a 2D torus. So this guy, so the graph is regular. Every guy has 4 neighbors. This guy sees this, that, and that. Okay. So 1, 2, 3, and 4. Okay. So what is the probability distribution? All we do is we go over the edges of the graph. You can think of this in general as a model on given any underlying geometry that is a finite graph. You run along the edges between nearest neighbors, and then you count a +1 if they agree, and a -1 if they disagree. Okay? You do that. This is the number of agreeing edges minus the number of disagreeing edges, and you multiply it by a scaling parameter beta that's going to play the role of the temperature in the system. And now you exponentiate, and you normalize it to make it into a probability distribution. This is it. Okay, so easing model. And as you can see,
What is X? Did Y neighbor or what?
a neighbor, yeah, so nearest neighbor. So as you can see, this is the easing model at different values of beta. As beta, the scaling parameter, is very, very small. Well, let's think of beta equals 0. Beta equals 0 means that we don't even look at our configuration. Every configuration gets a weight here of 1. And we just have the uniform distribution over the configuration with just the product measure of these Bernoullis. Now, if beta is close to 0, then we think that the spins are essentially independent. There will be some correlations, but they should exhibit an exponential tail. And what we see here isn't random. You see tiny, tiny clusters, but it looks kind of like noise. If beta is very, very large, okay, think of beta that is infinity, then you have a point mass on, well, you have everything plus and everything minus. Okay, these get weights, and then they have probability a half each. And if beta is very close to infinity, then you are suppressing disagreements. Sorry, that you are encouraging agreements, suppressing disagreements. That's right. Okay, and there is a critical point here that should correspond to this Curie point in nature, where you get neither the former nor the latter, and that will be the focus of this talk, but for the Potts model. Okay, so what is the Q-state Potts model? The underlying geometry is the same, the square grid, and the set of configurations is now giving us a color between 1 and Q possible colors to each state. Before we had Q equals 2, and now Q can be 3, 4. And the probability distribution is the same. There was a half before that was just a scaling, because this was the traditional way of writing the Ising model. Here we are, again, just summing indicators of agreements. Before I wrote a +1 if you agree and a -1 if you disagree, but it's all the same because we normalize anyway. So in both of these cases, we are just running along edges, and for each edge, checking whether its two endpoints have the same color. And if yes, if that's the case, we collect a 1. Otherwise, we don't collect anything, and we normalize it using this function z, that is the partition function.
But if it would be some matrix, it would be complete.
To calculate z.
Yeah.
Yes. So in this specific example, we have a 4x4. So we have 16 vertices, and there are if q equals 3, there are 3 to the 16 possibilities. And even though, for instance, if I look at this specific configuration, and I want to, thank you for the question. It's a good question. I have a specific configuration. I want to understand what I can from it, given this explicit formula, because it seems like I have everything I could possibly want. I have an explicit formulation for the probability distribution. It's true that if I look at the exponent here, it is easy to calculate. This is called the Hamiltonian. It is easy to look at the configuration and count the number of agreeing bonds. But in order to understand how popular or how unpopular this specific configuration is, I have to calculate this normalizer. And in order to calculate the normalizer, a naive method would be to just go over all the possible configurations, all the 3 to the 16 configurations, and for each one to calculate this weight so that I could know what to divide by. And that is hopeless when thinking, instead of a 4x4, this is nothing, I think this is I think 1,000 by 1,000. But even a 10 by a 10, that would be 3 to the 100. It's already unfeasible. Okay, so yeah, so what do? We still want to somehow understand. The question is, for instance, how do I know that this is what the model looks like on a 1,000 by 1,000? If I do not have access to this z, and therefore I cannot simulate the model. And to our rescue comes the family of MCMC, Markov Monte Carlo samplers, and specifically the one introduced by Glauber in the 60s is a particularly useful one. So here's how we can simulate these distributions, even if we do not have access to the partition function. We can select a site. Look at this area. We can select this purple site, and then just say that we're going to replace it by a color distributed according to the right distribution. We have our distribution in mind, call it mu. It's the Potts model for this graph. If I repeatedly select a site, erase its color, and then recolor it according to the marginal of the target distribution, given everything else staying the same, I am guaranteed to eventually converge to mu. Okay? Because if you did it from mu, then you would stay at mu. So the rule of this chain is mu is stationary for this rule, and you can get from any state to any state. There are no periodicity issues. It is irreducible. So So you have a natural sampler. And the main question is, how long does it take for the sampler to converge to mu? I have an aside here, by the way. What do I mean by sample it according to mu given everything else? The reason that Glauber dynamics is what it's called, or heat bath Glauber dynamics, Metropolis is also a version of it, that they are so common in practice, is that it's really 2 lines to implement it in code. Because how do you do it? You have this, let's go back for a second to the previous slide. We have this distribution. It had something that we do not understand, the partition function, and something that is easy to understand, e to the beta times the number of agreeing bonds. Okay, now, I want to understand how to color this guy, to recolor it. So I erase its color, I replace it by gray. And the point is that out of the, let's say that I have 4 colors. So out of these 4 colors, each of them is associated with a weight, and in each of them I divide by the same 1 over z that I do not know. But since I'm only changing this guy, then to understand the ratio of the probabilities of placing a different color here, I do not need to know what z is. It cancels out. The only thing that matters is e to the thing inside to that Hamiltonian. And moreover, that Hamiltonian that counts all the agreeing bonds is going to be comprised of stuff that's going to stay the same regardless of what I place here, right? Because whether or not there was a disagreement here does not depend on the color that I place in the center. And the only thing that it does depend on is the immediate neighbors of this gray vertex. So in other words, in order to understand the rule of how to recolor a vertex X, the only thing I need to do is look at the immediate neighbors of X. Okay, these guys, there are 3 blues and 1 purple. And then I know that if I place a purple, I get 1 agreement. If I place a blue, I get 3 agreements. And if I place a red or a green, I get none. So these are the weights of these 4 options. And now the probability of red is 1 over the sum. Probability of purple is e to the beta divided by this total sum, and so on. And that's it. Okay, so implementing this sampler really is elementary. You look at the nearest neighbors, and there's an explicit way to do it. And now you see how if I take beta to be extremely large, then I'm almost always taking the majority amongst my neighbors. And if there were 2 colors, suppose that this was split 2 to 2, then it would mean take the majority and break ties randomly. Okay? This is the behavior for beta that is very, very large. It's sort of like follow the majority of your neighbors. Here's an aside, by the way. If you actually did another tweak on majority of your neighbors, so let's say a majority of your neighbors, there's colors, and with some small probability, take a uniform color. Then I would not be able to analyze it, nor would anyone that studies these things, and we would not even be able to show a phase transition. So in some sense, these models that are so classical are the fact that we have an explicit formula for the final distribution means a lot, and we'll see that later on. Okay, so we established that we do converge. The sampler does converge to the target distribution mu, the Potts model. It is easy to implement, and the only question is, how many times will I have to update sites until I actually converge to equilibrium? So, and that's what we're trying to answer. Okay, there are a couple of slides here that are supposed to emphasize why in the easing model, there are various applications of the model that I somehow hinted at, where you could, you would model, I don't know, whether or not you believe that a stock will go, whether or not you believe that you should buy a stock or sell it, or there are applications in nature where you're trying to track genes and migration of genes, where the POTS model becomes relevant. I think that I won't elaborate on these examples just because I wanted to bring them in order to emphasize that the element of time, using the dynamics, it's not just that we want to sample from the POTS model. It is also the case that the POTS model or easing model in various cases are supposed to be toy models that are modeling a physical system, and we are interested in the dynamics where a site wakes up and redraws its opinion given its neighbors for the sake of understanding a natural evolution of that system, not just because we want to know how long it's going to take it to reach its equilibrium. We want to understand short time scales and what it behaves like if we start from specific starting states. Okay, so the dynamics itself is something that we wish to understand. Okay, let me show you.
But I suppose there are problems, so it's more interesting to try to convert to non-equilibrium. Right?
Yeah, you can ask about large deviations. You can ask, yeah. Here, let me show you for a second. This is, by the way, what happens if you run this dynamics. Run it at high temperature, and then, so this is for beta that is 0.5, and then I move beta to be about 2. That is twice the critical temperature for the free-state POTS model. So you see that sites immediately froze, and you get these dominant islands. And now I'll move it to 1, that is about the critical temperature. Okay? And around 1, we get things that look like they have fractal boundaries. And these are supposed to be SLE, but it is still not proven. Okay, for Q equals 3, it is conjectured. Okay. Okay, so we saw a little bit, we saw the dynamics of the POTS model in action. Let's see what we think about the answer to this last question, that is, how long is it's going to take us to converge to equilibrium. And I'm going to start with the easing model, because the easing model, that is just the special case Q equals 2 colors, is already non-trivial, and it will give us a hint of what we want to expect. We have the high temperature regime. So beta, remember, beta equals 0 is complete chaos, independence, complete independence. Beta that is infinity is just majority. Okay, so, and beta is the inverse temperature. So this is 0 temperature here and infinite temperature here. Okay. For beta that is less than beta C, than beta critical, the correlations between points should decay in the distance. How fast? That depends on whether you are red or green. But I should say that already just showing that, for instance, that in 3D there is an actual decay here to 0 was a major open problem that was settled only a few years ago by Dynamical, Eisenman, and Sidorovicius. Okay, and at low temperature, you do not do not lose your correlations. We'll say something about that soon. The expected behavior for the dynamics, you can measure convergence to equilibrium in many ways. One of them is just to think about this as an operator and look at its spectral gap. As just a stochastic matrix, it has an eigenvalue of 1 that is trivial because it's stochastic, and you look at the second eigenvalue. And you measure how big that gap is. That's and the inverse of that, the inverse of the gap is called the relaxation time often. So then in a nutshell, we expect that in the high temperature regime, we should converge to equilibrium in the single site heat bath dynamics very fast. The gap should be fixed. Okay? Just like if you have a finite graph, it's as if you have an expander graph. Okay? There's a constant spectral gap. At low temperature, you should be exponentially slow. So remember, the size of the system, even for the easing model, it's 2 to the number of sites. Okay, so exponentially slow in what is also a question. On an n by n grid, it should be 2 to the n, not 2 to the n. You'll have 2 to the n squared sites, 2 to the n squared states in your configuration on an n by n squared. It will be exponentially slow only as 2 to the n. But it's still very, very slow. Think of n being 1,000. And at criticality, you should have a power law. That is the conjecture. And it is more or less verified for the 2D easing model. We do not know the right power here. And here, actually the power, and that's something nice about it, is supposed to be universal. It should not matter if you have a square lattice, or a triangular lattice, or so in all of these 2D lattices, the location of what beta C is will move. That does depend on the geometry, but the 2D geometry will not change the exponent of n that you will see here in the dynamics. That is the conjecture. We are far from proving it, but at least we know that it's polynomial.
What about the boundary condition? So you had it on a torus, but what if you put it on a 2-hole torus or something? Would you expect that to change?
Thank you. Great question. For the easing model, okay, so here there's a big effect for the boundary condition at low temperature. Low temperature is kind of a different game. An all plus boundary condition will create a pressure on droplets to squeeze according to motion by mean curvature. Whereas a free boundary condition, you have a plus phase and a minus phase that are competing, and each one is unbreakable. Here and here, there should not be an effect of the boundary condition. Okay, but this is just for easing, and we'll see something about pots that is a little surprising in that regard.
Is there a conjecture to what the exponent is at
Yes.
criticality?
It should be 2.17. It's not a nice number. I mean, there are lots and lots and lots of simulations.
That's not expected to be rational necessarily.
The best lower bound is 1.75. It is it comes from looking at the test function that counts the number of spins, and and it should have been the right one because I mean, you can try various fancier lower bounds, and they are all coming short of even getting to 1.75. So you'd think that maybe, but all the simulations by physicists are give higher numbers. So.
Sorry, just from there, you were saying that at high temperature the convergence is fast.
Yeah.
But so I guess maybe is the inequality going the wrong way or something? Because I thought
It could be well.
beta less than beta C.
Yeah, that's high.
It's
Beta is
inverse
the
term.
inverse temperature.
Thank you.
Okay, so yeah, so it's 2.17 ... The high temperature regime was studied in a sequence of papers, actually going back to the 70s, 80s. The low temperature was settled in the 80s and mid-90s. For the upper bound on the power law, I mean, it's not just that we cannot show that it's universal. It's in this paper with Alan Sly, we had an upper bound that was, it is huge, humongous. So it is, and the method also is not, I mean, you cannot hope for the method to ever give you the right upper bound. Yeah, so something, the method was sort of a multi-scale analysis. You want to say that if you divide your square into two, you can bound, for every time that you divide your square into two sub-squares, you lose a constant factor. So using using SLE estimates, Usosim or Welsh type estimates that we heavily leaned on. And since you need to divide the square log many times in order to get to something constant, you lose that constant log n times. So it's constant to the log n, which is a polynomial. Okay, but the recursion is very wasteful. Still, it was the first time that we could get to a sub-exponential upper bound. Okay, what about the Potts model? Again, similar picture: high temperature, low temperature, critical temperature. Those of you who, some of you may notice that I tried to color this critical point in two colors. Okay, before we had a green for a power law. And it turns out that the Potts model, and that's what I was hinting at when I said that such a simple-looking generalization of the Ising model immediately comes packed with first/second-order phase transitions. It turns out that the number of colors matters. So for Q, this is Q, that is 2 colors, or 3 colors, or 4 colors, we expect a similar behavior to the Ising model. So let's look at, for instance, 3. It should be fast up until the critical point, then a critical power law that is universal, and physicists have simulations for those two, and they have simulations for them for various lattices and showing agreement. And then for beta that is greater than the beta critical, it should be exponentially slow. So this is for 2, 3, and 4. But for 5 and up, it is supposed to be the case, and now we know that at least in the static case, it is a very recent result that it's proven. For 5 and up, you should immediately consider yourself as if you're in the low temperature regime. So the critical point becomes a low temperature point where you should think of yourself as being exponentially slow instead of having a power law. Okay, so this is a first order phase transition at Q that is 5 and higher. And actually, if you really want, if you are really looking hard, you see that the blue line starts not here, but here. There is meaning to this model also for a fractional value of Q. You can make appropriate definitions. There's a counterpart model where Q that is 4.1 makes sense. And already, as long as Q is larger than 4, strictly larger than 4, you are in this phase where the critical point is a low temperature type point. Okay, so this is what we believe. Here's okay, so some previous works out of which I should highlight that in the low temperature regime, the right thing was known for Q that is large enough, okay, but not for Q equals, let's say, 5, 6, 10, okay, 15. For large enough Q, you knew that everything is slow, exponentially slow. And on the other hand, that was applied to ZD for NED. And similarly, at criticality, if Q is large enough, there's this paper by Borgs, Chase, Fries, Kim, Tatali, Goda, and Van Vu. And then later, a subset of the authors improved. They had an extra log in the exponent in the first paper that Borgs, Chase, and Tatali removed with a very delicate analysis. In any case, at the critical temperature, similarly, the result applied only for very large Q. And the fact that it applied to very large Q means that already you are only looking at the regime where the critical temperature is kind of a low temperature type. So they proved, again, an exponential lower bound on the inverse gap. So definitely Q that is 3, 4, and 5 were not yet accessible. And with my student Reza, we now know we are almost at the point where we are happy with respect to this question, in the sense that for Q equals 3, we get a polynomial upper bound, just like for Q equals 2. For Q equals 5 and higher, we have an exponential lower bound. So, so extending the range of the results of the papers that I listed below down to Q equals 5, and at Q equals 4, it is almost polynomial. It is n to the log n, quasi-polynomial. And there is a reason. The Q equals 4 case is extremely delicate. Already the static, because it is on the verge of breaking the second order phase transition and becoming a first order phase transition, it's the very nice SLE type behaviors of Q equals 2 and Q equals 3, they are no longer, it's no longer the case that you can enjoy all of these features at Q equals 4.
So if the graph that you have on the association,
yes,
change, then it's going to depend on the neighbors where the threshold is in terms of Q.
That's right. That's right. Okay, so let me show you very quickly. This is the Q equals 3 case at criticality. But for now on, let's just discuss the critical point. This is the critical point at Q equals 3, and you see that very quickly we converge to something that looks like, I guess, SLE. And let me pause that. And now let's look instead at Q equals 10. Okay, 10 colors. This is just to convince you. So you see, we very quickly, from a noisy initial state, we very quickly converge to something that already looks like it's close to equilibrium, whereas here, I can scroll very, very far into the future, and it still looks like nothing. I mean, it still looks like I started from all white, and I stay mostly all white with tiny islands that seem to have exponential tail. This looks like a low temperature system as opposed to a critical case. But of course, you see, if white is dominant here, there's nothing special about white. I mean, whatever weight the equilibrium gives white, it would give a state that is mostly blue. And that is the essence of this exponential bottleneck. Once you start with a dominant color, it takes over, and it's very hard to ever let go of control so that other colors can somehow become the rulers. And also, it kind of makes sense that you should have a phase transition. If you're thinking about this kind of heuristically, the more colors you have, the more, I mean, the harder it is to oppose a leader that has hard control, because all the other sides are somehow splitting in the votes between the different colors, and it's harder to arrange a majority of one color to somehow oppose the leader.
It's a multi-party parliament.
Yes. But okay, so so that was Q equals 3 versus Q equals 10. Okay, now, so now I did want to give you an essence of at least one of the proofs, and in order to do that, I thought I would focus on this one, on the lower bound that is exponential, but I can't really do that, so I will first just show those of you, I think some of you have not even seen the Peyer's argument that shows that the Post model even has a phase transition. And somehow seeing that can give you an essence of how the proof of this bound works, and then I'll sketch it. Okay, so I'll rigorously give you a complete proof of the beautiful argument of Peyer's that just shows that it goes back to the 1934, just shows you that the Ising model originally had a phase transition, and similarly the Potts one. And then you will be able to see how we approach this exponential lower bound, and then I'll end with something about what you asked about the torus. Okay, so going back to this Ising phase transition, the point in the Ising phase, why is this thing supposed to even model a magnet? I mean, you're giving pluses and minuses, and what is the point? The point is, you look at this model, and you impose a boundary condition that is plus. You fix these sites to be blue. Okay? That is my magnetic field. I mean, there are other ways to see this, but this is one way to see it. In one sense, is it a magnetic field? The sites right next to the boundary feel an effect towards being plus, because they have a fixed neighbor that is always plus. It's never changing. So they have a pull towards plus. Now, you let the size of the system go to infinity. There are just 4 n sites that are right next to the boundary, and there are n squared sites. Most of them are in the bulk, are far away from the boundary, and you're asking yourself, as n goes to infinity, they are becoming farther and farther away from the magnetic field. It's like turning it back off. And you're asking whether they remembered that they are close to that there was a magnetic field, whether they retained magnetism. So here are the two pictures. And here you see that, I mean, the border, okay, the frame is blue, but the sites very quickly forget that there's a blue frame, and here they do not. And formally, you let M be the sum of the spins. Okay, the magnetization, this is the test function that I was mentioning before. What is the average spin? So here in the Ising model, it's either 1 or -1. And we're asking ourselves whether it's 0. So before I placed a boundary condition of blue, everything was inversion invariant, because the number of disagreements does not change if I invert everything. So the mean of M was trivially 0. But adding this boundary of pluses possibly has an effect. And this is what's happening. The expectation of this average spin will go to 0 below beta critical and will stay positive, so bounded away from 0, if you are above beta critical. And that would capture ferromagnetism. Okay, so that was the motivation in introducing this model. And unfortunately, when Ising studied the model, he just wrote an exact solution in 1 dimension, bless you. And in 1 dimension, it turns out that if you put 2 pluses here and let the distance between them go to infinity, you're doing basically nothing, because, I mean, the information that you had a plus behind you can get erased with constant probability every time that you reveal the next spin. And once it's a minus, I mean, you are essentially you destroyed your boundary condition. So this is an intuition. You can exactly solve the model. It's just diagonalization of a matrix. And Ising showed that in 1 dimension, there is no phase transition. You can select beta to be a million or a bazillion, but putting 2 points as plus and plus and letting the distance between them go to infinity, the bulk is going to be to have mean 0. Okay, and this is a nice tidbit. In his paper, he also gave a heuristic argument showing that there won't be a phase transition in dimension 3, which is the actual thing, right? The magnet. So this was very disappointing. This is a copy. This is a letter by Ising. You see, I discussed the result with Professor Lenz. There was some disappointment that the linear model did not show the expected ferromagnetic properties. And Ising left research. and survived World War II in Luxembourg, and then came to the US. Okay, and meanwhile,
Do you know what this heuristic argument was?
I forget. I knew it once. It wasn't something that I mean, someone explained it to me once, and it was at least stated it once, and it wasn't something that made sense. But you know, but on the other hand, many physical arguments that are profound can also not make sense to me. Right? So, okay. Meanwhile, I mean, there were other models that were developed, and some of them led to beautiful and useful mathematical ideas. In 1936, actually not 34, but 36, Rudolf Peierls came up with this paper that actually sealed the model as being dubbed after Ising and not after Lenz, on Ising's model of ferromagnetism. And this showed that in dimensions 2, 3, or 4, dimensions 2 or higher, you do have a phase transition. And Peiers's argument is beautiful and it's robust. It applies to many other models and many other geometries, and it rests on the following. It's strictly combinatorial. So this would be a first moment calculation. So this is probabilistic combinatorics 101, in a sense. So what we have here, let's think about an Ising configuration. We have reds and blues, pluses and minuses, and we can toss in a dual edge whenever there's a disagreement between the two spins. Okay, so whenever you have a red and a blue that are adjacent, I'll place the dual edge to that edge along which there's a disagreement. And this creates a sequence of just a set of lines, contours. Now, if in the special case that we have a plus boundary condition, these lines, okay, that I draw here, cannot touch the boundary, right? Because the boundary is always full of agreements. So we have islands, closed contours, closed loops. There is an issue about how to actually break it into two loops when you have a plus. I did it like this. I always cut along the diagonal, along one diagonal. It doesn't really matter. Okay, so we have these islands of minuses inside the sea of pluses. And inside an island of minus, we can have further islands of pluses, and inside of them, further islands of minuses, and so on. And if I draw just the contours, because in the Ising model you just have two colors, this is telling us exactly what the original configuration is. So we can read the configuration just from all the nested contours. Okay? It's an equivalent representation. So what is the argument? Okay, let's look at this n by n box with an all plus boundary condition, just like we did. The argument rests on a bijection. I'm going to look at a green contour. Remember that a contour is this island of reds that is surrounded by my sea of blue. Fix this green contour. Okay, the bijection is specialized to this sea. So for every fixed contour that is this kind of loop, I'm going to tailor a dedicated bijection. So what is the dedicated bijection to this sea? Take the interior of C and flip it. So you see, every red inside becomes a blue. If I had something nested, then the nested becomes the guy becomes a red. That is the bijection. Okay, so why does this help us? The probability of this, suppose that sigma was a configuration that actually had this C as a contour. I mean, I just applied the map. The map works on any configuration. It doesn't need to look like this. Okay, the map, but let's just think of the effect of this map in case it so happens that C was a contour in this configuration. Then the original probability was 1 over the partition function times e to the something. Now, as soon as I made the flip, I destroyed the disagreements along the boundary of the contour C, because I made them all blue. Inside, I did not change the number of disagreements because I flipped everything. So a disagreement and an agreement both stayed the same. Okay, and outside, I also did not affect the number of disagreements. So the probability, whatever it was, is increased by a factor of e to the beta times the length of C. Whatever it was, I don't know what it was, but it's now bigger by e to the beta L, where L is the length of the boundary. Okay, so that means that if you look at if the green is the set of configurations where this is actually a contour, what we have here is a bijection, right? I know C, remember, C is fixed. So this is a bijection on the set of configurations, and it maps a set of configurations that has C as a contour to a disjoint set where it is not a contour, and that disjoint set is heavier by a factor of e to the beta L. Because every guy is mapped to a unique guy that is heavier by a factor of e to the beta L. That means that the entire green set is at most e to the minus beta L, regardless of anything else that happens outside of this green and the purple blobs. Okay, so this is what the argument showed. The probability that C is really a contour is e to the minus beta its length. And now we can finish the argument very quickly, because this is just repeating what we said before. How many sites does C actually contain in its interior? This is an isoperimetric inequality in Z2. It's L squared, right? At most L squared. Now, less than that, but we don't care about constants. And how many ways do we have to actually find a C of length L? You pick a starting point out of your n squared locations, and then you walk length L. So maybe 4 to the L, or 3 to the L, because you don't want to walk backwards. And I didn't even divide by L. I could have, because we want to end. I didn't impose that we want to end wherever we started, and there's double counting because of the starting position. Ignore all of that. N 3 to the L. Okay, n times 4 times 3 to the L minus 1, actually. So the expectation of the number of sites X that start as red. So what is the probability that a specific site is red? It has to be surrounded by a contour, right? So I just want to sum over the possible contours overall, and for each one, I'll count it as if all of their interior is red. Even though there can be nested guys inside, I don't care. I'll count all over all the C's. For each one, I'm saying in the event that it's a contour, I'll collect L squared. So you get L squared times n times 3 to the L times the probability that it's a contour, which is e to the minus beta L. And now we see that if beta is bigger than log 3, then we get here something, and let's say, take it to be slightly bigger, you get here something that is less than epsilon, or an appropriate beta. That means that the number of reds in the system is less than epsilon, the fraction of reds. Okay, so you have a phase transition. The boundary made an effect. So this is Peleris' argument. And this is a slide that I added, but I'll do it very quickly. And the thing extends to pots. You need to do something, because this is what I was talking about with the guys here before the lecture. I've never actually seen it, but you can just, instead of, you cannot invert anymore, because it's no longer a bijet. You don't have just 2 colors. You have Q colors. But you can select the color that is the most dominant along the boundary. You see the kind of, for a configuration, you look at that configuration, and you look at the color that is the dominant one along the boundary, okay? And you will, let's say you will make that one blue, okay? So you can always go back, and then you will get a constant fraction out of L, and it will again work. Okay, I will go back to this boundary. I will just say, okay, I was planning to say something about the lower bound, but instead of saying something about the lower bound, I will just stick to saying that you might have seen from the Spires argument that not only do we have a phase transition, a low temperature phase, but you see from this argument, the contours, so they are marking these islands within the sea of plus, and they have an exponential decay. So even though we are at low temperature, and at low temperature, I was kind of telling you that you should remember that you are plus. And that is true. You do remember that you are plus, but being in the same little island still incurs an exponential loss in the length of the island. So I'm trying to say, even though at low temperature there is a fixed correlation between these two spins, it is fixed because everything is either is blue or everything is red. Still, if I actually needed to mark the little islands of reds within the sea of blues or blues within the sea of reds, the probability that two guys will be in the same island does decay exponentially fast in the distance. And the way to formalize this is to look at the counterpart of the model that is the FK model that I'm not going to describe, but these crossings here are similar to those contours that we had over there in spirit. And what we were trying to say in the lower bound was to say that, for instance, if you have, since you have an exponential decay of correlations, it is highly unlikely to be able to destroy a crossing of reds chosen in a very particular way. Okay, I may, I'll be happy to discuss this offline in case anyone is interested. But I should just say that this lower bound builds on two beautiful papers by Domenico Pazzo, Sidorovicis, and Tassio, and this recent paper by Domenico Pa et al. And modulo those papers, our lower bound is actually quite short. It's about 2 pages. Okay, whereas these papers, these are extremely, the analysis here is extremely delicate and long. And once we know that, we can also extend the result. And instead of just getting, for instance, that at low temperature you are slow for Q large enough, you get it for free that for any Q larger than 1 at low temperature you are slow, and for any Q larger than 4 you are slow at criticality. Okay, so I just want to finish with one thing. And this is this question on what happens on the effect of boundary conditions. Remember this movie for 10 voters on the torus, that everything seemed like it's not changing, right? Slow. We proved slow mixing for 5 colors and up. Okay, what happens when we take, now instead of a torus, I'll take free boundary condition. So, I mean, maybe you'd say, well, if you force the boundary to be red, maybe something strange happens. But I'm not forcing the boundary to be anything. This is just the square grid instead of a torus. In the Ising model, the torus and the free boundary conditions are the same at low temperature and at high temperature. There's no special effect at low temperature for free versus torus. Okay, what happens here? Here, take this out. You can see, so 10 colors, you can see the colorful regime of disorder eroding from the boundary, where the boundary had just the free boundary condition, and it will relatively quickly take over everything, as opposed to. Okay, so this is the situation after you see, after I ran it for 10 minutes, and that was the situation here after 10 minutes. Okay, so so the obvious. Of course, I didn't run it until we actually tried to prove that in the free case, it should be like the torus, and then realized that, oh, actually it should be fast, and then we ran the simulation. So the theorem that we have is that under the free boundary condition, a faster version of the dynamics that I did not get into, but it is one that you usually use in order to avoid the bottleneck of this color rules or that color rules. It's one that is able to recolor colors in one go symmetrically, to switch from mostly reds to mostly blue in one go. So that version of the dynamics, which is fast also at low temperature easing, is fast here, even though in those papers by Bogues et al., it was shown to be slow. Already this cluster dynamics is slow at the critical temperature, and it's slow for us for Q at least 5. It is fast-ish if Q is large enough under free boundary conditions. And what is open is to show this, the same thing happens for the single site dynamics that we still cannot show. And this Q large enough should be 5 should do. Okay, there should be a so all of a sudden, so if you're not on the torus but you're on the free boundary condition setting, just a square grid, it should mix quickly. And I'll finish with that. Thank you.
So for time, so people maybe need to leave, then suggests that otherwise maybe there's some questions for.
Are there any applications of the Potts model to theoretical mathematics?
Yes, actually. First of all, because I'm actually very. Are we still? We are still recording. I'm very.
I can turn it off if you want.
I'm very happy that you ask it like that specifically, because that kind of implies that this seems like it's something of value to applied mathematics. Well, we are pure mathematicians, kind of by education, but the Potts model, if you want to forget about where it came from and forget about modeling and forget about applied math that uses this to I don't know, computer science and social community detection and so on, and you just want to think about the tools and the theorems. So the Potts model is the counterpart of something called the FK model, in the sense that there is one big distribution, and you can get from that couples the two, and it is very easy to get from Potts to this FK model and from FK back to Potts. The FK is a generalization of percolation, where you just have independent edges, and it tells you something about, instead of just having edges that are completely independent, you now induce some sort of a correlation between them, according to whether or not they are in the same connected component or not. So you're trying to build tools that will allow you to handle short-lived or maybe long-range correlations between indicators. Specifically, the easing model is the case Q equals 2, is one case where understanding the clusters of the easing model and showing the fact that Smirnov showed that it's a SLE. He did that using the FK representation, FK easing. And for the FK representation, Q is just a number. Q equals 2 is easing. Q equals 3 is another number where you can also expect to have SLE, but the methods of Q equals 2 no longer work. And one of the main reasons that the POTS model is so difficult to analyze is that when you just have two states, I'm sorry for the answer being so long, but when you just have two states, like in the easing model, you can order all the states. You have a natural ordering. We saw that kind of in piles. You have plus and minus. You put pluses always among minus, and you have a partial order. And all of these dynamics, they respect this monotonicity. If you start with something that is above something else, and you run the chain, it will stochastically dominate. The POTS model is the first case. You just add one more spin, and all of a sudden, all methods that rely on monotonicity break. And you have to go and search for something that would be more robust, that will not use monotonicity. Okay. I can talk about this for hours. Let's see.
What is Q here? Is correlation?
What is Q? Q was just the number of colors. So 2 for easing, 3 for POTS. No, it's actually, yeah, the exact same idea. Instead of encoding stuff in loops, you now have plaquettes, okay? And you just surround your islands of and you want to just it's just combinatorics. And that's right. It is messier. It is messier, but it was done, and it is not particularly painful. So it works, and it works for other spin systems. Random height functions. It's extremely useful. But that Peyer's argument is why I said at the beginning something about if you did different types of dynamics, then we won't be able to say anything. Is essentially our only way of showing a phase transition. So if you randomly perturb the system, the dynamics a little bit, it's supposed to convert to something that will look exactly the same. But since we don't have the formula for it, we can't do the Peyer's trick, and therefore our analysis of the low temperature regime collapses.
You showed that when for large Q, the free boundary condition, the simulation itself, the boundary. So does it show that a periodic structure? It forms the boundary.
I think the problem is that in the periodic case, the fact that lies underneath is that, and this is why there's the green dot of the green critical dot became blue. When it was green, there was just a disordered phase. The one that in this mesh of colors here. Think of this is a complete mess. This is disorder. That is always a phase. It's always a solution at the critical point. The point where you become blue is a point where you have this solution. This is a Gibbs state. It's a solution of it's an equilibrium state. But you also have a stable solution for each of the colors where it is dominant. And the fact is that the free boundary condition, even though it seems like you're doing nothing, because it seems like it's the torus, one way to think about this is that this free boundary condition will look like a percolation system in this dual model that I was mentioning, where you do nothing to the boundary. So it's free, so far so good. But this is the critical point, so it is self-dual. So it is dual to the situation where you have edges along the boundary everywhere. And if you have edges along the boundary, that feels like you are forcing a specific color. It's kind of a way to think about why free boundary does destabilize the solutions. And the only thing that you end up that you end up with is the disordered state. And that's why it invades from everywhere. This becomes unstable, as opposed to metastable. Okay.
Thank you very much.